fine structure. And then the surface cabinet add the word surface in front, ZACSAP. So I want to talk about first XAP, we talk about bulk first, and then later I will tell you how we can get the surface information from XAP. Okay? There's a school of information out there. If you look at this website, there's an organization that XAP organization that actually explain what XAP is all about in big gory detail. So here's the website itself. So you can go to this xap.org community. You can find all sort of information you need about XAP. Okay, so this is just for information detail. In future, in case you need to look up XAP, then you go to this information. It tells you about all the file structure. There are tutorial in the website and so forth. And calculation, how to calculate various structure that you see, and an example and things like this. So, okay. So that's a basic reference for XAP, very detailed type reference. But the first thing we want to talk about is actually the half of the XAP technique, which is based on photoelectric effect. So I would tell you about this, and this is nice because I would need to explain to you photoelectric effect when we talk about electronic structure determination later on in terms of XPS. So I'd like to sort of introduce you to it now so that you have some idea, and then when we talk about electronic structure determination, we know this what we're talking about. So XAP is caused by photoelectric effect. So that's point number one. And what is photoelectric effect? Photoelectric effect is simply you have photon into your material or molecule, you generate an ion, N+, and a photoelectron, so-called electron. So you have something neutral to begin with, the photon in, electron out technique. Okay? And this photon is absorbed completely by your target, which could be a surface or a sorbate on your target or on your system in the material that you want. And this photon has enough energy to ionize, to eject the electron. Because sometimes you have all done UV absorption spectroscopy, right? Whereby you send in your UV photon and you see peak from your solution and so forth. That's just absorption spectroscopy. It means that some of your molecule inside your solution get excited to an excited state, right? Get excited to an excited state. And how it get excited is because of the absorption of this photon, okay? If the photon energy is high enough, the absorption of photon not only excite the molecule to a bound state, but excite it to an ionic state. In other words, the neutral molecule become an ion plus an electron. Okay, so that's called photoelectric effect. So the photon energy is sufficient to cause an electron bound by the field within the target, so called binding energy. So it's the energy required to bind the electron. With a binding energy or ionization energy to be ejected, right? So it has so much, the photon energy is so great. Once it absorbs, the target absorbs the photon, it ejected this electron. The electron has to overcome the potential that is in, right? And then it has enough energy, this kinetic energy that you detect once you go outside the molecular field. So what have we got? We got, based on conservation energy, we have photon energy must equal to this energy that binds the electron inside your target, called binding energy, plus spare leftover energy that becomes just kinetic energy of this electron. So this is how fast it costs the speed of the electron. Okay? So this is the energy that it has to overcome, the electron has to overcome, plus the spare energy, which becomes kinetic energy of that photoelectron that comes. And this is the famous Einstein equation. This is the equation that got Einstein got Nobel Prize on relativity. That's not true. He never actually got a Nobel Prize on special relativity or relativity, although now he probably should get one because all your GPS system depends on special relativity. So, because if you don't include special relativity, the GPS system will be all wrong. Will not get you the right position. So he should have gotten a Nobel Prize on special relativity also, but he was ahead of his time, so nobody believed special relativity at the time. But a lot of people believe him about this equation. So he was able to explain what you see in this photoelectric effect. The innovation of this equation is not because Einstein come up with a conservation of energy. Essentially, there's no big deal. You look at this equation and say, well, this is just conservation of energy. What is the big deal about this notion of this photoelectric effect? The big deal actually is behind the scene. The big deal is that Einstein think of photon as a photon, right? So he's the guy who come up with the idea that this h mu here, mu represents the frequency, which you often think in terms of waves. He thinks that the photon is completely absorbed, so it's like a particle. So he was the guy who come up with the idea that, well, photon really is a particle. This light that you see, should be think of light a particle, should not be just think of as a wave phenomenon. So before his time, people often think of light as a wave phenomenon, but Einstein thinks, no, it has to be particle in order to explain this photoelectric effect. So a complete absorption of an entity called photon, and this is due to Einstein. So that's why he was given the Nobel Prize, is to change the way people think about nature, and this is how we think about nature. Light is no longer wave anymore, it could be photon, and that's Einstein. Okay, so experimentally, what do? We can control two things. We can control the photon energy, right? And we can measure the kinetic energy of the photoelectron. And if you know this and this, you can then find out the energy that binds the electron before it gets ejected. So this is known as the the binding energy that you have. So in simple MO theory, molecular orbital theory that we learned in first year chemistry, we can say that this binding energy, in fact, is the orbital energy. And if you make that assumption, you get the so-called Koopman's theorem. Koopman's is also a Nobel Prize winner. It's an interesting story behind Koopman. Koopman published a very short letter in I think 1937 or something like this, and stated, he basically makes one simple assumption. He said, well, let's just say that our ionization energy is the same as the orbital energy, right? After this equation come out, and that is known as Koopman's theorem. So it's a theorem that people assume is true. Then he gave up chemistry altogether and went into economics, and subsequently won Nobel Prize in economics. So he doesn't do chemistry anymore. He did economics. And this paper called Koopman's theorem is probably among one of the most referenced paper in X-ray photoelectron spectroscopy, because everybody start off with the Koopman's theorem. They assume this very simple assumption, very powerful. Everybody use that as a zero order approximation. But he was an economicist, so he got a Nobel Prize in doing that. Not doing chemistry, but doing economics instead. So what I said then is that if you know this binding energy, this binding energy turned out to be the band structure, the electronic band structure. As we'll see later on when we talk about electronic structure, later on, to obtain the electronic band structure as a function of momentum that we'll see later. Okay? So I'm going to stop here today, and then We'll talk a little bit more about photoelectric effect, and then the interference that give rise to the fine structure, and then maybe STM next time.